Hi, everybody. I'm Christine Flood, and I'm here to talk to you about why we really do need one more garbage collector in OpenJDK. And I can't get this there, so I'm going to hold on to it. Shenandoah has been going on for almost 4 years, and there have been a lot of people contributing to it over time. So I like to give credit where credit is due, and all these people have contributed along the way to getting it to the point where it is now. And many of them are up on the stage. This is Roman, Alexei, and Roland. What? Don't give me a hard time. Okay, so let's get started. I've never been to FOSDEM before, so I'm giving sort of all of the intro material to work up to where I want to be. So what is a garbage collector? And a garbage collector is sort of like an omniscient housekeeper, right? You bought these cookies, and they weren't good, they weren't bad, you're never going to eat them, you leave them in your pantry. And you've got this bread, and it's expired, but you didn't notice, and it's in your pantry, right? The garbage collector can go through and see all those things that you're never going to eat and get rid of them, and take the things that you do have and organize them for you. So running with managed memory really leaves you in a much better situation. Okay, so I'm going to jump into the current OpenJDK garbage collectors. I think that they all have a place. I know that there's sort of a support nightmare with these, but I wanted to say that in certain situations, I can see using all of them. So for example, if I was running in a containerized environment and I had 50 JVMs running on a server, I might want the smallest footprint, the single-threaded garbage collector that has no sort of wastage due to the algorithm. And that would be serial GC. If I was running something like a weather simulator and I needed the results fast, and throughput was what it was all about, I would want to use parallel GC. If I wanted to minimize pause times with the current OpenJDK garbage collectors, CMS does a young generation collection while the world stopped, but it never does old generation work while the world is stopped. So that can give you a minimal pause times, but it has some problems. Because it's a mark and sweep old generation, you can get fragmentation, and your performance can degrade over time. And if you want managed pause times with compaction, you want G1. G1 works very hard to be able to manage your pause times into whatever particular window you need. But for some folks, these aren't enough. Right? They have a heap that's too large and pause time constraints that are too small. And those are the folks that we aimed Shenandoah at. People that want to run 100 gigabyte heaps or 200 gigabyte heaps, but they still have to respond to things in 10 milliseconds. So if they know a request gets stalled because of a GC for a minute, then they've violated all kinds of quality of service guarantees. So I'm going to cut this one at the bud. Everybody asks me, why is this called Shenandoah? It's because the airport, PGC Airport, which is cool, that's the airport designation, is right outside of Shenandoah National Park. That's all. There's no big secret. It was just a cool little in-joke, and now you guys are all in on it. All right, so traditional collectors like the serial collector, parallel, Parnu, are all separated into generations. You have Eden, you have Survivor Space, you have Old Space. You have a card table over here, and what this does is summarizes old to young pointers. So you can collect just this part of the heap. Shenandoah doesn't use that. Shenandoah is a region-based garbage collector, and so is G1. What we do is we break up the heap into regions, and any of these regions can be either old or young, depending on, that point in time. So we'll start allocating in a region, and we'll allocate another region, and another region. Maybe we'll have a big object that's bigger than a single region. And then over time, those objects get turned into garbage. We'll pick the garbagiest regions, which are these two, and we'll compact them over there. And then we'll have free regions for you to allocate into. So it's a different, if what you learned in school was this traditional semi-spaces, it's slightly different, but not that different. Okay, so stop the world compaction. when I talked about compacting, those garbage collectors doing stop the world compaction, what they do is the Java threads run for a while, they stop, and then the GC threads do the compaction. And then they stop, and the Java threads start up again. Now, Shenandoah is a different beast, right? Shenandoah has, you run your Java threads for a while, you stop, you do a quick scan of the thread stacks, and then you start a concurrent mark, but you start the Java threads again. You do a quick stop, and scan of the thread stack, and you do a final mark, and then you do concurrent evacuation while the Java threads are running. So we have two very, very short pauses that are just as long as it takes to scan basically your thread stacks. So the concurrent marking part of that is a solved problem. CMS, G1, and Shenandoah all use basically the same snapshot at the beginning algorithm. All that means is that if you update a pointer, it used to point to bar and now it points to Baz. If you're in the middle of a concurrent marking cycle, you have to be sure that bar stays alive because it was alive at the beginning of concurrent marking. So all it is a barrier that adds bar to the things to be marked. Concurrent compaction, that's what Shenandoah does that's new. That's what's cool, is that we are able to compact the objects while the Java threads are running. So why is concurrent compaction so exciting? It's complicated, right? If you have several Java threads running that are all setting fields in an object, and the GC thread is going to copy the object, you can tell that there's all kinds of bad things that could happen, right? Somebody could write to it, and the GC thread could copy it, and we lose the update. Or these guys are writing to different copies. So what you really want to have happen is you want your object, all these threads to be pointing to foo, and then flip a switch and have them all be pointing to foo prime. And that way you don't lose anything and everything is good. But we can't really do this, right? Even if we had some sort of fancy-smancy transactional memory, just the time it would take to find all the threads that are referencing foo. And by the way, it's not just threads. It could be some objects very deep in the heap that are pointing to foo as well. Would all have to get updated at the same time, and we can't really do that. So the secret sauce in Shenandoah, which isn't really secret sauce, is that we've added an indirection pointer to every object. Now this is the scariest part about Shenandoah. I was afraid that we weren't going to get accepted because this pointer, we've increased the size of every object. But the power it gives you is worth it, right? Because you have these two threads that are pointing to foo. The garbage collector comes along, it makes a speculative copy of foo, and it does a cas to change the indirection pointer to point to foo prime. So anytime anybody accesses this object, before the cas, they get the old copy, and after the cas, they get the new copy. And it doesn't matter whether they're in another thread stack or they're somewhere deep in the heap, they're always going to have the current copy of foo. So what this means is that all object accesses have to go through a read barrier. Now this is the other bugaboo about Shenandoah, because the common wisdom back in the Lisp days was that reads are 7 times more prominent than writes, and so you can't afford a read barrier. But the reality is that our read barrier is extremely cheap. We have one hardware instruction, right? Before here, if you want to read a field in foo, you have to find the location of foo, add the field offset, and read that location. Here, we have to read the location -8, resolve that, and then read from there. So without Shenandoah on Intel, a get field is a single move. And with Shenandoah on Intel, we move the contents of the forwarding pointer into the register, and then we do the read of the value. So it really is one single machine instruction for a read barrier. And as I will show you later on, it is not cost prohibitive. There's still a race condition, if you're paying attention, right? Because we have one thread that resolves the forwarding pointer and then stalls out and writes to foo. And meanwhile, another thread copies foo. And this is a problem, so we also have to have a more complicated write barrier. We have a write barrier that copies the object first before you're allowed to write to it. So here you can see I've got A, B, and C over there. If I want to write to D, I have to first copy it over to 2-space and then write to it there. This isn't that painful, right? There are other collectors out there that are concurrent collectors, and they have to copy things on read. We don't have to copy things on read, we only copy them on writes. And writes are less frequent than reads. All right, and so our write barriers are pretty quick. These are ordered in this order for a complicated reason I won't go into. But we check the evac in progress thread, which is thread local, and we read the forwarding pointer. And if there is an evac in progress, we can just skip to the store. So our write barriers are fairly quick in the case where you aren't actually evacuating objects. And if you are, they just copy the object. They're fairly quick as well. So what do these barriers cost? They're not really as much as you might think. We have phases in C2 where, well, these guys are going to correct me. I'm not a C2 expert. But we can do elimination of barriers on new objects and null pointers. We can do read barrier eliminations on final fields. And we can, C2 already does barrier hoisting. So if you have a read barrier in a loop, it can sometimes hoist it out of the loop to make it less expensive. So I did a little experiment. This is from a paper I did last year where I ran some of the DiCapo benchmarks. And I gave them an incredibly large heap. I gave them a large enough heap that they never actually had to do any GC work. And these were the 3 benchmarks that were able to run in that environment. And you can see that comparing Shenandoah to G1, the overhead of Shenandoah was between 2.1 and 5.6%. This was a year ago. We have some numbers now where we're doing even better. Are there any other gotchas to be concerned with in Shenandoah? And you need to think about things like pointer comparisons, right? Because if I have an A here and it's pointing to A prime, if somebody has a pointer to the old object and somebody has a pointer to the new object, you can sometimes get something saying they're not equal when they are. So we compare the pointers directly, and if they're not equal, then we execute the right barrier on both of them. And then we can compare them both in 2-space and make sure that they're correct. And there's complications like this for things like CAS as well. I'm sorry? All right, volatiles. Everybody was all concerned about volatiles. Volatiles just create a new state, a new memory state, and we don't do any optimizations across them, and it's fine. I'm going to be really quick because we're going to do a demo afterwards. This is Elasticsearch. This is just, I wrote an Elasticsearch benchmark because I wanted to see. And the only thing that's really interesting here is you can see that this was also, again, from 2016. We were slightly slower in terms of runtime. But if you look at our total pause time in milliseconds compared to the other collectors, we rock. If you look at our max pause times and our average pause times, we also rock. If your main consideration is response time and you can't afford to pay for pauses, Shenandoah is huge. All right, I also ran a very famous warehouse benchmark just recently. And we actually, because of some excellent work that these guys have been doing lately in optimizing our concurrent marking, we are now winning both in terms of max JOPS and critical JOPS. So we beat G1 in this particular situation in both throughput and in response time, which is a huge win for us in terms of our getting better performance. All right, so we ship in Fedora. If you run Fedora 25, it's just -XX : use Shenandoah GC, and you can try it out in Java 8. We're scheduled to ship in the next release of RHEL. I can't promise that that's going to happen, but that's the current schedule. And we spent the last year working on productization and optimizations. We are much more stable, and we're getting much better performance. And if you have any questions, or if you want, to just send me email and I don't know, ask where we got the Shenandoah sweatshirts, go ahead. This is me. And I'm going to turn it over to Alexei, who's going to do the demo.
Nobody, yeah, all right. So obviously I did run my own benchmarks. Let's see. Come on. Nobody will believe you if you didn't run spec JBB on your product, right? Okay. Let's do this. Come on. Can you see it? Yes, you can. So shortly before New Year, Roman and I were having fun and actually written some visualizer tool which we will try to understand how Shenandoah works internally. It's just some eye candy. It turns out to be much more useful, not only for talks, but only to see how the collector actually works. So let's run spec.jbb under this visualizer, and Shenandoah is working. So what you see here, as Christine said, it is the regionalized collector, right? So this, what you see here, is actually the Java heap. The squares there are regions. They are color-coded to distinguish whether they are recently allocated, how much live data is there, et cetera, et cetera. Right now, spec.jbb ramps up, so it doesn't do any huge allocations at all. It just tries to figure out what's going on there. And there is a little graph on the top, which is kind of the time graph of these parameters there. So right now, nothing happens. We just do the heap work. And then something happens. Then we realize that we have to start the concurrent cycle. And the thing there on the top, in this yellowish, in the puke yellow color there, it is actually the concurrent mark phase, right? And the red kind of bar there following it, it is actually the concurrent evac. It's just to get you the feel about the size of these phases in your regular young GC workload, which mostly allocates, which doesn't retain much, et cetera, et cetera. But what you can also see there is that grayish line, which is the used heap, actually grows through the concurrent mark phase, thus saying that the allocator is still working while the collector marks. If you look closer at that graph, you can actually also see that during evac that also happens. But this is not the workload at which we will like to show the evac. For that, we have another workload. And this workload is really, really simple. I call it array fragger. You just say, I have the array, and at random index, I will just store the byte array there. This workload defies generational hypothesis because the oldest all objects died there. By the way, this is the characteristic which will be endemic for any in-memory, least recently used memory cache. So this is the simple workload that we can use there. And if we run Shenandoah with it, a few interesting things will happen. First of all, it has much higher allocation rate. And as it goes, you can see clearly that the oldest elements in the array gets rewritten. And so regions that were having lots of live objects will have less and less live objects, up to the point you have to deal with them somehow. In Shenandoah, that means that you will identify them as the regions with the most garbage, add them to the collection set, evacuate all the live objects from there, and move on. If you have the generational collectors, that kind of workload will just fragment your old generation. And you will face either the mixed pause, like in J1, or the full GC, like in parallel, et cetera. So this workload kind of tells you that we can survive this otherwise heavily fragmenting workload that defy generational hypothesis. Arguably, most of the data that people now store on heap are actually caches. So this is your go-to scenario. But you can clearly see how much those phases take. But we have the GC logs there. And if you look there, you can actually see what is the concurrent Shenandoah GC cycle. So this is the cycle number 55. And it has the pause init mark, which takes less than a millisecond, which we very fast scan the root set. Then it has concurrent mark. Any other concurrent GC does that. It takes 160 milliseconds. Then you have a very short final mark phase, 1.5 milliseconds. And those are the only pauses that are ever observed by the imitator. And this is where the Shenandoah beef is. You have the concurrent evacuation, which takes 200 milliseconds there. Any other collector in OpenJDK will have to stop to copy this object. So what the number that you're looking at there is your pause time. With Shenandoah, it's concurrent, so you don't experience this as much. So do we have time for other demos? All right. So So one of the things about this is that since you know that the most beefy GC policies are actually concurrent, that means you can run the collector back to back without much ill effect, right? The application would still run. For any other collector, that would be insane, right? If you run GC back to back, that means you always stopping the application for a long time. It has nothing to do there, right? It has no work to do there. For Shenandoah, we have a different heuristics that drive collections, and one of them that is very useful for testing is the heuristics that actually runs GC back to back. And you can clearly see that even though the collector is actually working very hard, so the concurrent mark and concurrent evac phases go back to back without stopping to breath, the allocator is still working. The application is still working, even though what you do is the back-to-back GCs. So this is how the good concurrent collector should behave, right? In the worst case, when you have so much garbage in the heap that you have to run GC back-to-back, your application still is able to run. OK? And the barriers, right? Christine told about the cost of the barriers. So let's run some application. Obviously, if you want to run throughput application, let's run Spig JVM, right? Let's get the classic thingy there. So if we run a single workload XML validation with the parallel collector, if you want to estimate the impact of barriers, we want a workload that does not retain much, and the XML validation does not retain much. It allocates and allocates not a lot. So GCs there are actually very, very short. So the performance of this workload is roughly, it correlates with the overhead of the barriers. With the parallel collector, you have only a simple interregional write barrier on the pointer store. So it's rather efficient there. And you have the workload that runs around 400 ops per minute, right? So if I run with J1, what would you say the performance would be? What would you expect from J1 at this workload? Who's 400 out there? So 4x performance hit. 200, 300, 400, 500. Oh, come on, you're not fun. OK. So with J1, if you run this, you will actually see that because it has to do more heavyweight write barriers there, it would actually run slower. This is the warm-up, so we didn't care about this yet. But it will sustain the throughput of 320 ops per minute. And this tells you something important and fundamental about GCs. If your application does not care about pauses, then well-engineered throughput collector will beat you every time. So only if you care about the pause time, it makes sense to run the concurrent collector regardless of whether it's fully concurrent or partially concurrent, et cetera. So it's 330 ops per minute. So how about Shenandoah? So who's saying that Shenandoah would be slower than J1? Of course it would be. Who's for faster? Of course, yes. So for Shenandoah, you have the write barriers for every write, not only for the pointer writes, and you have the read barriers, right? So you can think that if read barriers are very expensive, then you will see an enormous performance impact, right? But it turns out it's not really that bad. So J1 made 330 operations per minute, and we are doing 320, I think, operations per minute there. So the cost of read barriers, when your read barriers are really, really basic in implementation-wise, is really not that high. All right? But again, if your workload is purely throughput, you don't care about post times, you can afford larger GC pauses, then you shouldn't really bother. You should just run with parallel old and be happy about it. OK? Yes, you want to talk about the pauses?
Open the floor for questions.
Yeah, questions. Cool. Oh no, not Azul, not Azul. Azul is banned to ask questions. Yeah.
Go ahead, you.
This is when you talked about the location of the, so creating a new pointer to kind of.
So there was a talk about the new pointer you create when you delete the old object, and my question is about a VM or a process running about a year or so. How do you think this iterations over creating new pointers, what would be the impact on the objects? Would it is this solved, or is this?
So you're asking what happens with the previous copy of the object? Is that what you're
So
asking?
no, if we create a new object to kind of solve the problem that threads or any other objects could not find the new object, we create a new pointer, if I understood correctly.
Every object has an associated forwarding point.
Exactly. So this is one iteration on one garbage collection. If the process or whatever, it goes for about a year, I think creating a new object. So after each garbage collection, you would create a new pointer, right?
No. When
Okay.
you collect the from region, the old pointers go, the forwarding pointer has the same lifetime as the object. So when you have copied an object to space and given it an informant, you copy the object to space, you go through the next phase where you do the concurrent marking, and you make sure all your pointers now point to the space copy. And then that previous version can get garbage collected.
Okay,
So there's no keeping of historical forwarding pointers.
I see. Okay.
Yeah.
Thank you.
So do you support both C1 and C2?
Yes. An interpreter to boot.
All right. Mary, you're kicking us off.
Cool.